All right then, let's move on. We're looking at the next lesson, and we'll be doing some lab work next week. I just didn't have time last night with parent-teacher interviews to set up a lab. But that's okay. We've got lots of time next week. We've looked at Newton's first law of motion. We looked yesterday at Newton's second law of motion, which is going to get more involved. The applications of Newton's second law of motion will get more complicated. Okay? And we'll come back to that starting sometime next week. Now we have to look at what is called Newton's third law of motion. So we want to be able to have a qualitative understanding of it so we can describe and explain what it means. And then we need to apply Newton's third law of motion in two situations today. One is to find speeds. Newton's third law of motion can be used to determine the recoil speed or the recoil velocity of a rifle when you fire a bullet. You understand whether you fired a handgun or a rifle or a firearm of any kind or not, that when you pull the trigger, there's a little explosion that pushes the bullet out of the barrel, but the whole gun goes backwards, right? People who don't understand that, and you can find lots of videos online to laugh at them, are people who hold the rifle. I'm acutely aware this is not a rifle, okay? To hold the rifle here and pull the trigger. The rifle may only move back at a meter per second or so, but if you have a 5-kilogram rifle that hits you in the head moving at 1 meter per second, it's going to leave more than a mark, okay? Probably leave a concussion. We're also going to use Newton's third law of motion to find what are called reaction forces. So what Newton's first law is an object will remain at a constant velocity unless acted on by an unbalanced force. I don't think I've gotten around to fixing your note package. The word force appears twice in there. It's just grammatically it doesn't make sense. I think I was probably typing it out and said unbalanced force and then went, oh no, net force, but I forgot to get rid of the word force. An unbalanced force is simply a force that is not counteracted by an equal or opposite or an equal force in the opposite direction. Let me say that again. An unbalanced force is simply some force that's applied to the object somehow that isn't canceled by an opposing force of the same value. Newton's second law of motion, there's not much to say. It's really a formula. Newton's second law of motion is an equation. Okay. So both of these laws describe what happens to an object. And this is going to be something you will really grapple with a lot in Physics 30, the first unit of Physics 30. That when we talk about the acceleration and the net force, we're talking about the acceleration of a single object and the net force on the single object. So as an illustration here, if you talk about a falling apple, we can analyze the forces acting on the apple. That's a fact. And a falling apple, I'm not going to embarrass myself by trying to draw an apple. A falling apple would have a couple of forces acting on it. One would be a force of gravity, and one would be a force of friction with the air, which is opposing gravity, right? But the fact of the matter is the apple is attracted to the earth. It is, that's a fact. That's why an apple falls. But forces don't happen by themselves. They don't happen in isolation. If the apple is attracted to the earth is attracted to the apple. They pull each other towards each other. If friction is pushing the apple up, then the apple is pushing the air down as it moves through the air. And it's very often to analyze the forces in isolation, which is what we've done. This is an analysis of the forces in isolation. We're just looking at the forces acting on one of the two players. But it's also useful sometimes to analyze the forces between the two players. And I'll give you another example in a second. Another example that I think makes more sense than the ones I have here. When describing the acceleration of the car, we've only been looking at the forces on the car, not the forces that the car exerts on its surroundings. A perfect example is this. when I'm playing baseball and somebody throws a pitch to me and I hit the ball, there's a collision between the bat and the ball. Would you agree the velocity of the ball changes? So the velocity of the ball changes tells us that there's an acceleration of the ball, which means there's a net force acting on the ball. Yes? The net force is caused by the bat hitting the ball. So if the ball is coming towards you, the net force on the ball is away from you, which explains why the ball slows down to a stop and then speeds up in the other direction. But I hope, if you've ever played baseball, you probably don't even have to, you can imagine it, that you understand when you swing that bat and that bat is moving maybe at 12 meters per second just before it hits the ball, that the bat doesn't continue to move at 12 meters per second. The bat slows down. Why? Because the ball is exerting a force, a net force on the bat. So the bat accelerates towards you, which means it slows down. If you don't swing the bat enough, the bat will slow down to a stop and then come back. But the bottom line is during that collision, this is the important part. The ball exerts a force on the bat, and the bat exerts a force on the ball. And this is what Newton's third law is all tied up in. And this is true for collisions or any time objects are in contact with each other, which is whenever you hit a force. I cannot force this tape measure. I'm sorry, I can't do it with my mind, right? It doesn't work. I've tried. I need to make contact with it. So an acceleration can only happen when there's a second object causing the acceleration. And what I'm telling you, Newton's third law is saying, if I apply a force of half a Newton on this to the right, it is pushing back on my hand with half a Newton. I can feel it pushing against my fingertips. So if object A exerts a force on object B, then B must exert a force on object A that is equal in magnitude and opposite in direction. In other words, the net force of the ball-bat system is zero. The ball experiences a net force which causes it to accelerate in one direction. The bat experiences a net force which causes it to accelerate in the other direction, but the two forces that cause those accelerations cancel. If you were to look at both of them together, the net force is zero. So, examples. And when we solve these, there's no formula for Newton's third law. We have to reason out what's going on. While standing on a horizontal frictionless surface, so this is an ideal situation, but it prepares you for real situations in 30. A 50-kilogram student pushes against a wall with an average force of 125 newtons east for 0.110 seconds. What is the velocity of the student at the end of that time? Okay, so, you know, I'm standing here on a frictionless surface, and I'm going to imagine it's 1.1 seconds. I'm going to do this in slow motion. So I'm here, and I apply a force, and it's frictionless, so I'm going to move backwards, right? And I'm going to go from not moving to moving. And then I let go. During that not moving to moving, during that 0.11 seconds, we can go with 0.11 because that's what it is, I accelerated. Why did I accelerate? Because there was a force being applied to me. Read the question carefully. Does it say anywhere in here what the force applied to me is? Does it say the student is forced with so many newtons? No. But if I push towards the wall with 125 newtons east, the wall pushes me back with 125 newtons west. So the net force on the wall is 125 newtons east. I am very aware that many of you could just take the numbers out of the question and work with formulas and get the answer, but it's going to get more complicated later, okay? This is not the force on me. I want to find my velocity at the end. I want to find, or the students, I want to find VF of the student after 0.11 seconds. And actually, I don't know that many of you could just use formulas to answer this. There's something else involved here. So we have a net force on the wall of that. How are we going to end up solving this problem? Well, we're going to understand that the net force on the student is going to be 125 newtons west. And you know, I get that you're probably looking at this and going, well, could we solve the problem without even worrying about this net force on the wall? Yes, but not for very long. Okay? For other questions you can. Would you agree that VI of the student is 0? And would you agree the time is 0.11 seconds? So we have two kinematics descriptors. VI is 0, t equals 0.11. That's not enough to find VF. So how are we going to find VF here? What are we going to do? Get the acceleration using what? Not kinematics. F net equals ma. Because we know the net force acting on the student. We know that this is equal to, we know that that 125 newtons, I'm going to leave the directions out of it. We know it's west, right? We know that. Is equal to the mass of the student times the magnitude of the acceleration of the student. And unless my brain is totally shut down, I believe when you take 125 divided by 50, you get 2.5. So the student accelerates at 2.5 meters per second squared, and that will be west because the force, the net force on the student is west. And the net force on the student is west because the force on the other player is east. And now it's a matter of just using, I guess, the kinematics formula. Acceleration equals VF minus VI over t. Sometimes I worry about me saying, oh, we don't need vectors, because maybe a student might not understand when we do and when we don't. If you're unsure, always put vectors. We don't need them in this case, though. So we can put in 2.5 equals VF, which is what we're after, minus VI, which is 0, over 0.11 seconds. I hope you see when you multiply the meters per second squared by the seconds, you'll get meters per second. Yeah?
If something's 0, do you have to write the units for it?
No, that's a good question, actually. Because you notice since this started yesterday, I started putting units in everywhere. And what Sam's asking is, do you need to put meters per second squared here? And I would say no. You know, in my mind, you could just do that. You know, of course, when you get to post-secondary, you're going to encounter a whole group of interesting characters in terms of teachers and lab assistants and stuff, and they all have these quirky rules, and somebody might come along and say, well, it's 0 what? You need to put meters per second. But I don't care. When we multiply that, do you get 2.75? Okay. So the final speed is 2.75 meters per second, and as a velocity, it will be west. Are we okay with that? I'm hensing that it's not 2.75, because I asked that and somebody nodded, and then the rest of you kind of looked at me. Is it 2.75? 0.75. Thank you. 0.275. So we're good with 0.275 then. Okay. Thank you, Sukhman. So any questions with 1? All right. So now we finally get, I've talked about this before, that you're going to encounter physics problems where the formula is not on your formula sheet. Like this previous question, the formulas were all there, right? You used F net equals MA, there's a formula you used. Then we used A equals VF minus VI over T. That was a formula. Well, you can't solve this with a formula. So a student stands on a frictionless skating rink and throws a 5 kilogram ball east at 10 meters per second. This is equivalent to me saying a rifle is fired and the bullet goes with a particular speed. What's the recoil speed of the rifle? Well, this is asking what's the recoil speed of the student? And this is complicated because the student and the object, ball, 5 kilogram ball, it's a pretty heavy ball, are connected, and the student pushes the ball in one direction while the ball pushes the student in the other direction, and during a certain period of time they both accelerate. And they stop accelerating when they leave contact. So if I'm going to stand on a frictionless surface and I start here and I throw this tape dispenser to the back of the room, what's going to happen is as soon as I start pushing it forward, I'm going to start moving back. I'm going to accelerate backwards. This is going to accelerate forward. And those accelerations will continue because the forces continue until I let it go. And the instant I let it go, that has a final velocity to the back of the room, and I have a final velocity to the front of the room. So there's a period of time over which this happens, but you're not told the time. So how do we do this? What we do is this, and I'm going to write something that's wrong and ask you to identify what's wrong with it. I'm saying that the net force that the student exerts on the ball is equal to the net force that the ball exerts on the student. That's what that says. But it's wrong. And I was going to say it's technically wrong, but that's the worst kind of wrong. Technically wrong is wrong. Well, it's not technically 120 volts, but go ahead and try it anyway. We don't want to do that. What's wrong? Right, these directions are in different directions. And sometimes in this course, in this unit, we can go ahead and say one force equals another. But more often than not, what we have to say is the magnitudes of the two forces are equal. And what that means is the mass of the ball times the acceleration of the ball. And I hope you'll forgive me that I've gone over this a number of times where I say, if you don't want the vector, put the vector symbol in the absolute value signs. Are you okay with me just writing A with no vector symbol? It's the magnitude of the acceleration. Has to equal the mass of the student times the acceleration of the student. Well, that's kind of useless because we don't know any of the accelerations. But we're going to go a step further. And we're going to say the mass of the ball multiplied by VF minus VI over T of the ball. That's how we find acceleration, right? I'll just write that on the side here. Acceleration is change in velocity over time. I'm just doing a substitution, right? Any place I see A, I can put this thing in. And now I have equals the mass of the student times VF minus VI over T of the student. And I'm going to simplify this in steps because I understand, it's early in grade 11. You've not got a lot of algebraic skills, some of you. Your algebra and math is lacking now, and that's not a criticism or anything. It's just that's the reality of semester 1. So the next step is to say the mass of the ball times the final speed of the ball over the time equals the mass of the student times the final, this is of the ball, times the final speed over the time of the student. Why? Because the student is standing initially at rest when they throw the object. So at that instant in time, just as the force is being applied initially, neither of the objects have yet begun to move. VI is 0 for both. And then I'm going to do this. I'm going to forget about the time. Wow, I'm going to cancel the time. I'm going to multiply both sides of the equation by t to cancel the t. Now, the final velocity of the ball is not going to be the same as the final velocity of the student. It's not. But the time that the ball was being forced is the same as the time the student was being forced. Because the force started when they were in contact with each other, and as soon as that contact was released, the force ended. So however long the student was pushing the ball, that was the same length of time the ball was pushing the student. And when we solve this kind of question in Physics 30, we bypass all of this and use a different physics idea. But the bottom line is now we can answer the question. I can take the mass of the student. Ephraim, was it 50? 75? And we're trying to find the speed of the, 75 kilograms. We're trying to find the speed afterwards of the student, I believe, yes? It was a 5 kilogram ball, and it was thrown at 10 meters per second. So 5 kilograms times 10 meters per second. I hope you see when we divide both sides by 75 kilograms, your units will be meters per second. So do me a favor and take 5 times 10 divided by 75 and confirm that you get 0.6 repeating. Are these numbers right that I put? Okay. I think you'll get 0.6 repeating. You end up, forgetting about units, you end up with this little equation. You end up with 50 equals 75x, so you divide both sides by 75. You get 2/3 or 0.67. So the speed of the student afterwards is 0.67 meters per second, and it will be in the opposite direction. If you're asked for the velocity, then you have to go back up and look at these directions and say, the ball was thrown east, the student is going to be moving west. I'm just going to throw a question out there. I'm not going to dwell on it. Not even a question, a statement. Compare the two masses. Compare the two masses. And when we compare things, we don't subtract. You don't say the student is 70 kilograms more than the mass of the ball. How many times as massive as the ball is the student? And I think it's 15, isn't it? The student is 15 times more massive, and the force acting on them results in an acceleration that gives us a final speed that's going to be 1/15 as fast as the speed of the ball. Right? When you fire a bullet that moves out of a rifle at 800 meters per second, you know the rifle doesn't come back at 800 meters per second. The reason it comes back so much slower is it has to do with the mass. The net force is related to the mass. Net force acting on the student results in a little acceleration. That same net force acting on the ball results in a greater acceleration, which explains the two speeds. Okay? Let's skip 3. I don't know why I put 3 in there. I think I put it in there with the intention of doing something else with that distance, but we would solve it in the same way we did example 2. This is a difficult problem, these problems, and we may just do this one and not the next one, because there's a lot to unpack here. And then on Monday we can do the next one. We are a little bit behind or a little bit ahead in the course, so we've got time to relax and go slow. Three boxes, A, B, and C, are positioned next to each other, and they're on a horizontal, frictionless surface. What's going to make example 5 more complicated is we're not going to use frictionless. We'll have friction. You know frictionless is a fairy tale, right? Okay, it's just what we do so we can learn the basics of physics, and then we wake up and go, wow, geez, there's friction. What are we going to do? And we figure it out then. Can you confirm that the masses of the 3 boxes on your diagram are the same as this one? Because I retyped it and formatted here. Okay. And can you confirm that the person pushes on box A, which is connected to B and C? Well, they're not connected like glued together, but they're touching each other, right? Can you confirm that the acceleration is 2.4 meters per second squared to the right? Okay. So we are asked to find all kinds of things here. So first of all, forgetting about the numbers, would you agree that the hand applies a force to box A? Right? Would you agree then that A applies a force to the hand? And those two forces are equal but opposite. Don't try to overanalyze this just yet. Would you agree that there is a force on B to the right? What is exerting the force on B to the right? Box A. The hand's not touching B. A is touching B. But that means if A is pushing B to the right, B is pushing A back to the left. And again, it's going to seem like we're running in circles here, but we're not. It'll all come together. Is there a force on C to the right? Well, there has to be because it accelerates to the right. What is exerting the force on C to the right? Box B. But that means that box B must be experiencing a force to the left due to box C. There's a lot to keep track of here. So I've put this in the order that I think is helpful, except for maybe near the end. What is the force that C, what is the force on C applied by B? When you take a look at C, we're getting into some pretty complicated things. When you take a look at C in isolation, what are all of the forces acting on C? So let's get something out of the way right now so we don't have to keep repeating it. Is there a force of gravity on C? Yes. Is there an equal but opposite force on C, which we call we talked about normal force, right? Is there a normal force? Yes. What do they add together to give? 0. So the thing I want to get out of the way right now is for this example, I'm not going to worry about those forces. We could do the same for B and the same for A. We don't need to consider them. And what this means, everybody, is that when you look at C, there is only one force acting on C. And it is the force on C by B. It's no good to just say it's the force between C and B, because we're talking about the force on C. There is only one force acting on C. There are 2 others, but they add to give 0. So, why? Well, I'll write it. Whoops. Is this a true statement? You have to read it in the subscripts and think of it carefully. Is the net force on C the same as the force on C due to B? Yes, it is. Why? The answer to this question is crucial for so many things that we're leading up to in this unit. Why is the net force on C equal to the force on C by B? Do you know, Colin?
The only unbalanced force is being applied by B.
Beautifully put. It's the only unbalanced force. Had you said it's the only force, I would have said, well, there are two other forces, but they're balanced. The bottom line is, even if I do include this force of gravity and this normal force up, this force is the net force, because when you add those three forces together, that's what you're left with. The rest is unbalanced. Well, we can find that. We can just say that the net force will be equal to ma. We just need to take the mass of c and multiply by its acceleration, which we know is 2.4 meters per second squared. And we will get the force on c by b. And of course, it will be to the right, because c is accelerating to the right. So what do we have? 4 kilograms multiplied by 2.4 meters per second squared is the force on c by b, which is 9.6 newtons. Help me out here. Just make sure that 4 times 2.4 is 9.6. Okay. 9.6 newtons to the right. Now, you have a lot of space there. I hope you're reserving some of it for the rest of the question. So this is 9.8 newtons right. What is the force on B applied by C? 9.6, right? Okay. Thank you. I can always tell when somebody turns around that I've written something down wrong. 9.6 newtons to the right is the force on C by B. Well, what is the force on B applied by C? It's 9.6 newtons left, because of Newton's third law of motion. Now, does B, which is experiencing a force of 9.6 newtons to the left, does it accelerate to the left? No, it accelerates to the right. So how are we going to find the force on B by A? We're going to draw a free body diagram. Okay, so what I drew here to explain what we did to find that first force, we have to repeat it now for the middle box. It's a little too small. There we go. We're going to repeat it for the middle box. So the middle box is on a horizontal frictionless surface. And, again, I'm going to draw a free body diagram. But because there's so much to unpack here, I'm going to simplify it. Is there a force of gravity acting down? Does it play a role in what's going to happen here? No, because it's counteracted by the equal but opposite normal force. So I'm not going to draw them. What I am drawing are only the horizontal forces. We already know that there is a force, this is B, right? There is a force on B by C of 9.6 newtons to the left. But we know that the person is pushing all three boxes, so they all move to the right with an acceleration, right? 2.4 meters per second squared. How is it that B is being pushed backwards and yet accelerating forward? Well, the answer is that there must be a forward force greater than the opposing force. This is the force. This is the force by C. I'm not going to say on B because the B is right there in the diagram. This is the force by A. It has to be the force by A, because A is the only thing that's pushing it to the right. And A is pushing it to the right because I'm pushing A to the right. We don't know what this is. That's what we are asked to find here, right here. What is the force on B applied by A? But we know that the net force equals MA, and we know, and here's the first time you're going to see something like this, that the net force is the same. Well, I guess I have to, we've got to do this properly. We know that the magnitude of the net force is the magnitude of the force to the right minus the magnitude of the force to the left. In other words, the net force, everybody, you can not write this down if you like. Just hold off on writing it down. This on the left is true. It is true. The net force is found by adding the forces together. But since they're in opposite directions, it's found by subtracting the magnitudes. And I always want us, for the rest of this unit, when we analyze free body diagrams, to do this. To say the net force is the bigger force minus the opposing force in the other direction. Both of these things are true, but I think it's better to write this. So, what do? Well, this is MA. This is 9 kilograms times 2.4 meters per second squared. This is what we are trying to find. And this is 9.6 newtons. Minus 9.6 newtons. Can anybody confirm this is 21.6 newtons? Okay. So what do you have to do to both sides of this equation to get that force that we're after now? We have to add 9.6 newtons. Okay. So when we add 9.6 newtons, what do we get? Is it 30.2 or 31.2? 31.2 newtons. And this will be, this is the magnitude of the force on B by A. You may be bummed out at having to write this on B by A, but I think it's important. It's not just the force, it's a descriptor to it. So that's 31.2 newtons, and that is on B by A, which is to the right. And we're just going to take a little break here so I can ask you to think about something. If the net force on B, everybody, you need to think carefully about this. If this is the net force on B, which is the force, the net force needed for it to accelerate at 2.4, why isn't this the answer to the question? Why is the actual force applied to B from the left 9.6 newtons more than what is needed? The answer is because you have 9.6 newtons opposing that because C is pushing it backwards. So you have to apply that 9.6 and then any additional force goes into the acceleration. All right, we're almost there. What is the force now on A applied by B? Well, Newton's, I got to get this here, there we go. Newton's third law of motion says the force applied on A by B will be equal but opposite to the force applied on B by A. Which means if A is pushing B 31.2 newtons to the right, B is pushing A 31.2 newtons to the left. One more step here. What about the force that the hand applies to A? So when we found this, we drew a free body diagram for box C because we were analyzing the forces on C. When we found this, we drew a free body diagram for box A because we were looking at the forces on, for box B because we were looking at the forces on box B. Here, we need to draw a free body diagram. We'll actually do this one first. We'll draw a free body diagram for box A to determine the forces acting on A. It is confusing, yes? It's not simple. When I say it's confusing, I hope you're not confused and you're following everything I'm saying. But you understand if you have to do this on your own, it might be confusing. So now I'm going to draw box A. So this is now A. I can get rid of this. So, what are all of the forces acting on box A? Well, there's a force of gravity down, there's a normal force up, they're a wash. Let's not waste our time with them. There is a force on A backwards of 31.2 newtons. Correct? I just need to say, this diagram is not scaled the same way the other diagrams were. Right? I mean, if you look at this diagram here, 9.6 newtons looks to be longer than that. This is just a free body diagram on its own. But we know that there is an acceleration of 2.4 meters per second squared that away. And if there's already a force acting on A to the left, there must be an additional force acting on A to the right. That's the force exerted on A by the hand. This is the force on A by B. This will be the force on A by the hand. And it has to be greater than 31.2, otherwise box A wouldn't accelerate to the right. The net force has to be in the direction of the acceleration. So how are we going to solve this? Well, we're going to say MA of the box. Well, I better not do that. We're going to say the net force on the box will have a magnitude equal to the force on the box, box A by the hand, minus the magnitude of the force on box A by B. And how many of you are getting the idea here that whatever MA is for box A, it's going to be greater than that to get the effect because we have to overcome that opposing force. So now it is, I think it was 7 kilograms. Yep. Now it is 7 kilograms multiplied by 2.4 meters per second squared. So the net force is MA. That equals what we are after, which is the force on A by the hand, minus 31.2 newtons. Thank you. And you can confirm that this is 16.8 newtons, somebody? Okay. So the answer to the question will be whatever 16.8 plus 31.2 is, and by my count that gives 48 newtons. Now, we're done the question. Okay, well, I guess not quite. 48 newtons, right? Which means the force on the hand by A will be 48 newtons left. We're done the question. Are we okay with that? But I want you to do a calculation for me. Let's say, I told you these boxes were not stuck together. They're just touching each other. Well, imagine that they are stuck together. Imagine I glued them together. So there's really only one object. And the force of 48 newtons is being applied to that one object. What will the acceleration of the object be? Well, as a whole, F net will equal that 48 newtons. Like if you just look at this whole thing, there is a force on the whole thing of 48 newtons. And that has to be equal to MA. And the mass of this is 20 kilograms. So what do you get for the acceleration when you apply F net equals ma to the whole thing? You get 2.4. But if we're interested in dissecting it and saying, well, what are these individual forces that are all acting in combination with each other, we have to look at 3 separate free body diagram and force analyses. So we're not going to do the next one, which is what happens if there is a force of friction. And usually I limit it to only 2 boxes if there's friction. We'll do that one next week. Okay. In the meantime, it's not 1 to 7, it's 1 to 6, because 7 is one that involves the boxes with friction.